Well, good morning. So this is week 14, lecture A. And we don't have a lecture B because Wednesday lecture is canceled. So it's a new class day. So today is November 25th. So November 27th, we have a new class. Okay? So we don't have B here. So next Monday will be December 2nd and December 4th, and 9th and 11th. Okay, 11th. So these are the residual 4 lectures. Okay, 4 lectures. All right. So today our main topic is to focus on optimal control. Okay, optimal control. Because from our from our ME212, the title is robust and optimal control, right? Robust and optimal control. Optimal control. So we have learned H2 and H infinity kind of optimal control. It is optimal in the sense of TZ, W, J omega. That kind of norm, okay? That kind of norm. Either in 2 norm or in H infinity norm, okay? Okay. So that's from in and out performance index, okay? Remember, we use Z and W W is introduced to make a assessment of the performance variable Z, so TZW. So, but from another point of view is from what we call dynamic optimization point of view. Okay, dynamic optimization point of view. In other words, I have a system following XUT, right? So this is my dynamic evolution. And of course, I have x0, xt0 is x0, okay? Initial value problem. So it's a control function, okay? Now my control, of course, control is u bar and u underbar and u bar in this interval, okay? This interval. So of course, x can be vector, okay? So my job is to find out the u of t, okay? U of t. I didn't say u of x, okay? I didn't say u of x, okay? I didn't say that, okay? Not yet. So optimal control means I have a j, which is function of my ut, okay? Okay. I want to minimize this ut, okay? Minimize this ut. Such that, so this one is usually in the sense of like t0 to tf, final time. And usually you put a performance index L that is xut dt. Okay, that's my cost. Okay, that's my cost. So we want to minimize something. So be careful, okay? I want to minimize something, okay? So it is itself is a function. So it's a function of function, okay? Can you see that? So function of function. So this is a function of t, right? This is a function of u. So it's a function of function. So therefore, people call this is a functional, okay? Functional. Okay, functional. So remember, I have infinite number of points on this curve, u of t. Infinite number, okay? So basically, you need to find out the infinite number of, if you parameterize it, so it's an infinite dimensional minimization problem. Make sense? So it's a much harder problem. I call this is a dynamic optimization instead of static. Because this nature, okay, this nature, because of this nature. So it turns out that everything we learn from here, okay, in a specific case, we can talk about LQR problem, linear quadratic regulator problem. In a very specific case, say for example, L XUT is written as X transpose QX plus U transpose RU. So this is a cost, this is a penalty to the states. So then what you are going to do is X transpose QX plus U transpose RU. And you do DTT and then T0 TF. And this is your JXUT. Okay? JXUT. And your subject to your original system is X is AX plus BU. So this is, we talk about LTI system, okay? Of course, it's by default is a minor, okay? The reason LQR is nice is because they can take care of the MIMO automatically. Multiple input and multiple output. Is that right? So that's why LQR is useful. So you can see this is a special case of this general case. Okay? I want you to learn in generous case, whatever F you put it here, whatever error you put it here, I always can solve it, at least numerically. Okay? So there is a magical, I still feel like this is a world class solver. It's called, right. Okay. Of course, I know this topic pretty well. More than 20 years ago, okay? More than 20 years ago. Actually, I started looking into this one in 1995. In 1997, it is the first time I made this as a MATLAB toolbox that can be run on the Windows platform. And we maintain that. And I checked last night, and everything's still working in our latest version of MATLAB. So I zipped everything you should be able to do in 2019B version, okay? For the MATLAB. Everything should work. So this is the only package in the world that you can solve OCP problems, optimal control problems, without code compiling. Okay? In other packages, you have to compile the code, link your code to the given library, and forming an executable code. Then you run your program. So this is very beautiful, very beautiful, especially good for beginners. Okay, good for beginners. Okay, so this is called M file interface. I said you don't have to compiling. That doesn't mean you don't need to do coding. Okay, be careful. Coding is different to compiling in a sense. You write a code, you run the code. That's via an interpreter like Python. Okay, you didn't compile code. So, but when the program is large scale, it could be slow. Okay, so yet you still need to have something called C file interface. We have that. Okay, but you don't do it in this lab form. Okay, you don't do it. You only use M file interface. Okay, M file interface. I checked the speed, M file interface versus C file interface. The speed is 30x. Okay, 30 times difference. Okay, so I'm going to solve that one. So today, I'm going to give you a background about the formulation of general passive optimal control problem, how you can look at this, okay? Then on the way, we are going to look into this one and how this one we are going to solve this one leading to what? Algebraic Ricard equation. Okay? So how we derive it? Okay, how to derive it? There are multiple ways to derive the LQR. Okay? LQR. Multiple ways to derive it. So multiple ways. And using the optimal control point of view is the way we should learn. While most schools in their curriculums, they no longer talk about Pontryagin's maximum principle. We do not talk about this anymore. So I want to make sure you get this message. And everything we do in Arias is actually based on this one. Okay? Based on this one. Okay. So with that, I hope you have a pretty good idea of what we are going to cover. And you know what we're going to happen this week. This is week 14 and week 16. So week 16, I think week 16, 15 is the last day for lectures. Is that right?
Mm-hmm.
So basically we should have this one, this one, this one, this one. We have 4 left, do we? I don't think it's a good idea I gave you all the lectures. So I think it's a good idea. I use this as a week to do fraction order optimal control problems for you and fraction order system modeling. And these we give you for some relief, okay? And remember, 20s is the ultimate deadline of everything. And I think it's fair that I only give you 3 homeworks and 5 labs. And it's 4 credit course, so it's pretty reasonable, right? But you still owe me something called presentation, okay? I target this day for a presentation, I'm hoping, okay? So let me think about it. I already drafted FISP specs. What you should do. Don't worry too much. Align your research with this course, robust and optimal control. You don't open a new topic, okay? Try to align with your own research. And for all of you getting credits, you must do the presentation. For those of you, you are invited to join us to give a presentation aligned with your research interests. Okay, so that's going to happen in the rest of the semester. And today I'll be here until late, so welcome to visit my office. So with that, I'm going to do the slides and so how many of you can give me a good guess what is this one? Called recursive integration optimal trajectory solver, okay? Right. So I purposely put integer order is to make you aware that in our group, in UC Merced in general, we should distinguish between integer order and fraction order. I hope next week after the Thanksgiving, when you come back, I'll give you enough dosage of fractional order optimal control problems, okay? So I want you to be careful about this word. It's called general. Then you should ask, really, how general is general, okay? So let's see how general the problem is. So what we are trying to do here is to give you a little bit of dosage of calculus variations. How we do the derivation of, I said, you do minimization here, u of t, there are infinitely many points of this curve, right? So it's infinite dimensional. So it's a functional minimization problem. You search not on a Euclidean space like Rn, right? So you are searching on a functional space. So instead of searching a set of parameters, you are searching a curve among many, infinitely many curves. So then we need a new tool. That tool is called calculus variation. I'll go through that. Then for general integer order optimization problems, what's the solution procedure based on Pontryagin maximum principle here? Okay, we're going to talk about it. Pontryagin. I have Pontryagins original book in my office in Kassel. It's I have Bodhi's original book. And we're going to visit the LQR problem as a special case. So then you will say, wow, everything we learn is a subset. But let me remind you. What we're doing is u of t. Okay, u of t. We're not talking about u of x. U of t is a control signal. What does that mean? Meaning everything we do here is you put it here, you get output. That's called open loop. Open loop. Remember, when we say optimal control problem, it is open loop. Okay, open loop. But in the end, we actually want u of x. That's called control law or feedback. Because you measure the x, then you construct the u. That becomes feedback control. Feedback control. So regarding the LQR happens to be a feedback control, okay? So they have that kind of nature, very beautiful. We'll see today. Then I'm going to walk you through the code, so minimizing your time reading the menus, do a lot of things. We'll see how much time we have left, okay? I already prepared all the demos, okay? So, let's start with static optimization, okay? Here, Rn, so x and u are parameters, okay? They are parameters, there's no t here, okay? So we basically are searching for static parameters. So then we define Hamiltonian with Lagrangian multiplier, okay? This is a Lagrangian multiplier. So what's the stationary condition meaning? It's sufficient condition, okay? Sufficient. So it has to be, this has to be like that, or necessary condition. But there may be exceptions, okay? There are exceptions, necessary conditions. So must satisfy means necessary condition, okay? So meaning you have three things here, then partial of this will be, partial h, partial lambda will give f left, so it's 0. But we know that f is 0. What is f is 0? This is called constraints, okay? So this is called equality constraints, okay? F is a function, okay? So to consider the constraints, if f is not 0, then I penalize you. It's something like a penalty function, penalize. So then partial h, partial lambda, you give f is 0. This is nothing but this subject to this constraint, it's the same. Then partial h, partial x, you are going to get partial L, partial x, partial f, partial lambda is 0. Okay? Because lambda is a parameter, is a constant. Okay? It's a variable. We don't have any t in here. Okay? So that's why it's static. So all these things are just that we have commonly done like multi-variable calculus. Okay? So it's called stationary condition. Stationary condition. And the introduction of this one is just redundant. So this one has to be 0. If it's not 0, you add it to the edge. Okay? It's like a penalty. Okay? Like a penalty. So this static optimization, I think everybody is very clear. So stationary condition. But what if we have dynamic optimization? I use a dynamic optimization here. I told you I have a time history, okay, of the state. Okay, Rn, everything is a time history. They follow this differential equation as the time evolution. But how to choose the U, depending on how you choose, your performance index will be different. I care only from T0 to capital T. T0 to capital T, okay? Capital T. So then this is a function, okay, for index. So this is integration of that. So this is called terminal cost. Terminal cost, meaning when your system evolved to time capital T, then the state and time constructed with function phi as a terminal cost. So this is called terminal cost. But there are also other constraints in the terminal constraints. So the terminal state and terminal time must form a kind of equation. Let me give you an example, okay? So you have a ball, I have a robot hand, I want to reach the ball. Of course, when you reach the ball, your ball has to be on the ball. The point is not inside the ball, you break it. So that's a constraint. You know? This is a constraint. In the end of your reach, okay? You have to be there. It's not going there, right? So there you control it such that in the end, you should be there. And also you should say, oh, my time cannot be longer than that. So faster, okay? So that kind of terminal state, they call final state, I use terminal state, it's the same. So this is very general setting, And so some cost function idea like minimum energy, minimum fuel. So I perform this such that my energy consumption is small. Minimum time, you just integrate that. Okay, so this is LQR, Q and R. So this is the fuel, this is your state, okay? So this is called minimum energy problem. And there's a terminal cost, okay? So you can terminal cost. But the terminal cost is interesting, they put the same R in here. Is this really necessary? I don't think so, okay? It's not really, it happens to be like that. So it's not necessary. But usually you just say, oh, I don't care, whatever your terminal is called, free terminal. Free terminal, it doesn't care about your terminal state. Then it's fine. So you remove this one, this is 0. Okay? That's called free terminal. So to solve this problem, as I told you that we are trying to find out, the minimum U of t to make this minimized, okay? Performance index. Remember, we put the capital T in here. So it's called terminal time. It's possible that the terminal time is free. It's possible, okay? It's terminal free. So I don't care. I don't have this capital T here. I give you the capital T. I give you. okay? But there are cases you don't even know when to stop. The capital T is not known in advance. The terminal capital T depends on what you put the U here. Let me give you a Goddard problem. Goddard problem is a rocket, and you have fuel, and how you burn the fuel to push it, okay? Then they will reach to the highest possible height, okay? Then the time reaching to the peak point will depend on how you burn it, how you burn the fuel, okay? The fuel, the burning rate, okay? You can control the burning rate. Then that's the optimal control. Then capital T, you don't know what is this, but I do know capital T is a function of U. Make sense? Capital T is also a function of U, depending on what you put the thrust. We're going to see that. So in this case, it's called free terminal time case. Okay, free terminal time case. So to do that, we need to make a simple introduction of calculus of variation. So it's called functional. It's not a function of scalar variables like previously we have seen. In new mathematical tools called calculus of variation. And we want to understand what is considered as a variation of xt. So you have a curve, x of t is a curve, okay? But if I shake it a little bit, just change a little bit, so it's called variation of the curve, xt. It's called small delta, okay? But there are different things about differentiation regarding displacement and total differentiation and so on and so forth. So we are going to look into this picture, okay? Look at this picture. So you have original function x of t in here, okay? Then suddenly your x will be perturbed by dxt. Remember, when we say dxt, it doesn't mean I end up with the capital T. The end, this end, and this end, this end, and this end. So originally it's here, and after the variation, it becomes here. So the beginning and ending point should also change. Okay, you know. Okay, so therefore we need to make a distinguishing point in here. So this is called d capital T. So the terminal time changes, okay? Terminal time changes. Initial time, of course, we start from initial time, okay? But initial state is different, okay? So we have this dashed line, okay? Dashed line. Then we want to understand what is the dx capital T, okay? Here, so what is a, so from here to here, so this is called dx capital T, okay? So this, the terminal point, the total variation. It is actually a delta xt, okay? What is a delta xt? Is here, this point. So this is my delta xt, small delta xt, okay? And what is the other one? The other part? The other part is nothing but the dt times the tangent at x dot capital T. X dot capital T. Okay? So this type of variation with endpoint also changing. So they have this type of relationship. Okay? Relationship. I think it's quite intuitive and visual. Okay? Leibniz said, if you have a function implicitly in here, what you can do about dj, the variation, okay? Differentiation of the dj. Actually, we call this is a total differentiation, okay? What we should do is, you cannot say like, oh, dj is partial partial x, partial j partial x. The dj is partial the dx, dj dx. They put this dx this side. Okay, so it is a partial in here, and you have delta x. Okay, you have delta x. And you also need to consider the terminal, okay, the terminal. So that's, Leibniz already did that kind of variation, okay, variation. So refer to this curve, refer to this equation. It's not too hard to understand this, okay. You have functional, okay, you have functional. I want to understand if my x has delta x has a variation, how this delta x will lead to my variation in j. Remember, j is also a function. So I have function change in here, then what is the other function change in here? Leibniz rule gives this equality.
Can I see the previous state once more?
That is for a single function itself. Is assuming the assuming you have a delta x here, and what are all these relationships? So we should not confine as the same endpoint. The endpoint is also changing. Fine. Okay. Let's assume this is true. It is true. Long time ago, Leibniz derived that. So here is something I want to show you. Okay. So what we basically want to do is, I have a function. I have terminal time, I have control, terminal cost. This is an integration of my cost. This is my considered as constraints. This is my dynamic equation. This is my equality constraints in the terminal. So what we do is we just throw everything into the same. So we'll copy here. So this one is here, okay? But phi is 0, okay? Phi is 0, put it here. So the new here is a penalty, or sometimes it's called Lagrange multiplier, okay? But on the other hand, inside of L, let's add a 0. So this f minus x dot is nothing but what? 0, okay? So this is 0 actually, make sense? 0 times anything is still the same. So this idea is from Lagrange multiplier, okay? So this equation and this one is the same, they didn't change, okay? But j prime, if they are not 0 for some reason, the j prime will not be the same as j, okay? So how we move forward is introducing the Hamiltonian function. So again, we just pull out the Lagrangian and multiplier here. So like L and lambda is my Lagrangian multiplier, okay? So if we do, we belong to these two as H. This is a copy, the same. And here is terminal cost and terminal constraints, multipliers. So what do we do here? Okay, we use that Leibniz rule and make a total variation here in J prime, how to do that. So there's a very mathy equation here, okay? So here we can do integration by parts. You are going to have something like this, okay, something like this. Don't worry, we just make sure that we take care of this term. Oh no, delta x dot is this term. This term. So this term. So this integration, okay, is possible to do integration by parts. And remember, we have this magic equation. So in the end, we have this total variation in J written in this long equation. But remember, all these here are terminal, related to terminal cost. So So in fact, a lot of people ignore this because if the terminal is free, everything will be zero in here. Okay? I don't care about terminal cost. Okay? But otherwise, it is quite complicated to make everything correct in here. It's very easy to make mistakes. Okay? I saw a lot of people made a lot of errors in here. Even in integer order case. Okay? In fraction order case, this is still very complicated for people to make things right. So let's go back and find out. The stationary point is to make this guy 0. Okay, make this guy 0. So make this guy 0. So then we have what we have here. So this is a state equation. This is cost with terminal constraints. State equation will get partial h, partial lambda. H is L minus lambda transpose f. Okay. Let me recall. H is L plus lambda transpose f. Okay. So then partial h, partial lambda is f. Then they can say lambda dot is partial h, partial x. How this is true? This is from here. Okay, so it's from here. So also delta, all these are variations. It's arbitrary. Okay, arbitrary. To make this 0, then this must be 0. Understand? So this one has to be 0, this one has to be 0, this one has to be 0. Because delta x, delta u, delta lambda are arbitrary, okay, can arbitrarily chosen. So you set this one 0, then these must be 0. So that's why for the first one, h x lambda dot is 0, you need to h x lambda dot 0 equals 0. So this is called co-state equation or adjoint equation. Partial f, h you know that is f plus lambda transpose L. So partial x, partial f, partial x, lambda, and partial L, partial x. Okay? Then you look at this HU is 0. Okay? So HU is 0. This one must be 0. H is L lambda transpose F, so you have transpose F partial U, and you got this one. Okay? So then if you check this one is nothing but state equation. Okay? So you have state equation here. X dot is F. Is that X dot is F. Okay? So we have discussed this part. Okay? This is giving us the way to solve the equation. But the rest part is called transversality. So this put it to 0. We need to analyze it very carefully. Okay? Capital T and dxt, they are not dependent, are not independent. So you cannot simply say, oh, because of that, this one can be set to 0. It's not true. Okay, it's not true. Only when you have fixed final state, or fixed final state, then fixed final state, then there's no change. It's fixed final state. Say, for example, I reach the robot hand to the board to that point. That's a fixed point. So there's no variation here. It's 0. So in that case, life is easier. Or you fix final time, given time to the given point. That will make these two guys to 0. That will make this one much more simplified. Okay, simplified. But if not 0, life is very complicated. You have to analyze it very carefully because they are not independent. What does that mean? That means, so these and these are not related. So because this one can change arbitrarily, thus to make this one 0, this has to be 0, this has to be 0, this has to be, so that this can change independently and arbitrarily. Make sense? So with that, we need to make this guy 0 and this guy 0. Okay, so to make dj prime 0, so that's a stationary point. But we already are enough here. Okay, we can run this example. I'll go very quickly. This is a very simple example. Okay, so you have ambient temperature, current temperature, and your temperature change is, if you don't have this one, your temperature will drop until your theta is theta A. So then the theta dot is 0. Okay, but I want to heat up or cool down, then I need to add a control. B is A and B are two non-constants. So what do? We can define, oh, this is x, okay? X dot is theta dot, so this is x dot minus. So this is a very simple first order system, right? Okay, so let's do this. We assume that I have a minimum energy controlling here, but I have a terminal cost. The S is just a constant, okay? Weighting constant. It's not a function, it's a constant.
So the capital T is a constant or not?
Capital T is also given, okay?
Is it constant or not constant?
Constant. Capital T is giving, it's fixed time. So this is an important term. Fixed, okay? It's giving. So then we check, so this L function is half of the L. Lambda times, what's this? This is x dot.
F of x.
F of x.
That's.
X dot minus fx. Sorry.
No, that's f of x.
Lambda f, okay?
Yeah,
So this is f. This is f. L plus lambda transpose f. So this is f. X dot is f, okay? So by doing that, we check what is my control U to make this one small. So then we solve x dot is ax. So this is the original function. Lambda dot is minus h partial s, so it's a lambda. And 0 is hu is u plus b lambda, okay? So remember, lambda is called Kerr-state. Simple, right? Simple. But, so we can do like optimal control from this stationary point is b lambda. And b lambda, we just can get this, okay? So to get the u star, we need to only find out what is lambda, okay? What is the best lambda, okay? But the Kerr-state is lambda dot is a lambda, okay? And x dot is ax minus b squared lambda, okay? So that's not very hard because x0 is also given when t is 0 is given, okay? So remember, you just stack x and then lambda as a vector, so you have a differential equation of vector form, okay? But you have half of the vector is giving initial point, okay? But we don't know what is this guy's bond initial condition or any condition, okay? It turns out that very interesting. I told you 2-point boundary value problem. So this is the initial value problem. This is final value problem. Okay. So we'll see. So because of this boundary condition, fixed time dt is 0, okay? So we don't care about this. So new final state constraints, okay? So therefore, lambda t is partial phi partial t. Then this s is a constant, xt minus 10. It is it is a fixed t, okay? Fixed t is a lambda t, okay? Lambda t, okay? Lambda t. So lambda t is given, okay? Xt, okay? Xt is dependent on x0, okay? And xt also dependent on the control. A control is dependent on lambda, so it's all tangled, isn't it? Okay. So however, we can consider to solve, because lambda t is none, okay? Lambda t is none. So in other words, in this differential equation, we don't know lambda 0, but we do know lambda capital T. So you have to go from lambda capital T to lambda 0. So that is giving a lambda T, giving the terminal value, lambda capital T, and what is the lambda T? So then you reverse the time. Did you see the reverse time? Okay. You go time backwards from capital T to 0. Okay? Your system is moving from capital T to 0 here. Okay? But of course you can use lambda T0. So we put this lambda t we already solved into xt. Xt is a b times, so go back a few slides. Yeah, ut is minus b lambda t. Well, b used is b square lambda t, okay? B square lambda t is lambda capital T and this guy. So it's reverse time, remember. So we solve this one. We are going to get xt, something like this. Okay. There are some hyper sign. Okay. That doesn't matter. Okay. So these are all giving. These are all giving. Everything is good. I have a curve of xt. So then we use this one. We can solve what is my x capital T. Okay. So x capital T based on that is given by this, okay? Capital T. So assume that x0 is 0 degree, and lambda capital T now we can solve it like this one. It's a function of a, b, and s, okay? A, b, and s. Okay, a, b, and s. And with this lambda t, then you have a lambda star t here. So this is your final value. So the optimal control U star is something like this. A, B, S, and e to the power of AT. So that's our optimal heating. Okay, optimal heating. So even for this simplest trivial problem, we need to solve this 2-point boundary value problem. Even for very simple CP problem. In most cases, we have to rely on numerical method. So this one is an analytical method, okay? So we need to use values. So closed loop optimal control problem. So far we solved this U of t is an optimal control signal. It's not control law. So we are going to take a look at LQR. And we are trying to solve open loop problem, okay, optimal U of t. But we end up getting a closed loop solution. That's the beauty of LQR, okay? So let's take a look. So this is easy for everybody. So Q, R, and S are just weighting matrices. So this is a state cost, this is a control cost, this is terminal state, energy, okay? So of course, all these things are symmetric, positive semi-definite. So we can mimic something called energy, okay? And we have finite time t0 to capital T. And we assume t is fixed at this moment. And also x of t is free, it's free. I don't care, meaning s is 0, okay? S is 0. I don't care about my state. So what I do is, I end up with ax minus b is r inverse b lambda, and lambda is this one. So this is a state and co-state equation. Of course, you can do this is L. This is L lambda f, lambda transpose f, you can do those Pontryagin's maximum principle to derive all these things. Okay. So that is our state and co-state equation. And the control input is a function of lambda, as we have seen before. And the terminal condition is here, could be 0. Okay. Terminal cost. Okay, terminal cost. So then it's very interesting. Okay, this was bothering me a lot. By writing lambda t as function, as a linear function of xt, they said, hey, let's simply write lambda t is this way. So it's assumption. It was assumption. It's not a fact. Later on, people happen to find it is okay. It is a good guess. So this is a guesswork at this point. Okay, it's a guesswork. Remember, but it's a good guess. This st is different to the s here. It's different. Okay. So then we try to basically say, oh, assume this is a like time varying gain in here. So remember, if lambda right in this one is like a state feedback with time varying gain. Okay. If you insert it into there, you get something like that. So, but how to find out this time varying gain? You just put things like lambda dot. You do lambda dot, you will have s dot x, x dot. Then s dot x, keep it. Then x dot, you know this is thing, okay? Remember, this is R inverse B, lambda is sx. So you write something like this. And so then you remove the x to the other side. So you end up, let me go back a slide. So you remove this guy to this side. This one is different one in here. So we get, and we get this one, okay, and this one. So this is true for all of x. This is an interesting argument. So therefore, we can remove the x. So this one must be like this. So I hope you understand this is what? This is a Riccardi differential equation, RDE, okay? So the optimal controller is written a time varying gain, okay? So this is also called common gain, KT is this one, okay? I don't think this is x, there's no x. And people say that, oh, don't worry, that we can compute this KT offline, okay? So here's Pontryagin minimum or maximum principle.
But LQR, I mean, we cannot use, I mean, it's not related to Riot's toolbox in any way, is it? I mean.
Oh, I just show you that the Riot can be used to solve this problem as well.
Riot can be used to define the same objective function,
yes.
But then it's not going to be LQR because what Riot solves is just open loop optimal control problem. But LQR is supposed to be.
Yeah,
I mean, what we mean is just that we choose the same objective function as LQR has, right?
Yes,
is
we just to basically use the same idea to derive Riccardi differential equation based. Okay. So it's not necessarily we are trying to do a Riot. It's next slide. Pontryagin maximum principle. It's basically saying that optimal control problem depends on the stationarity condition, partial H, partial U is 0. So it's a necessary condition. Okay? So control U, constraint lying at the admissible region defined by a requirement that is magnitude be less than a given value, is bounded. The control is bounded. This is always true in practice.
Yeah.
You don't have a huge control authority over the control system. So then we assume that so admissible U means is within the bound, okay, within bound. You cannot have the authority to be over that control limit. So remember, remember, you have a star means they're already at the optimal solution. Okay, then whatever control you, even in the admissible feasible region, then this Hamiltonian is always bigger than the optimal value, optimal value. So that's proven by Pontiac. That looks very simple, which is what we exactly need. Okay. So if it's not at the minimum, then it will be bigger. Okay, it will be bigger. So it's called maximum principle, sometimes called minimum principle. Okay. Well, what's the difference between maximum and the minimum? You put a different sign here, a negative sign, right? So here's a very interesting Newton's law. This is what? This is a double integrator. Input, integration twice. Okay? So our job is, just think about you have a mass, you want to apply force to that, so that I want to go from 0 to capital T in minimum possible time under the constraints you push or pull using its effort is plus or minus, within plus or minus 1. So that's called bump control, bump control. So in this way, how to solve the bump control? Okay. So you have terminal constraints, okay? You have to go from rest to rest, okay? So they have x1 capital T, x2 capital T, all both 0, meaning they are in a rest state. x1 is, x2 is speed, okay? x2 dot is acceleration. So x1 is displacement, x2 is speed, okay? Displacement and speed, at the end, both 0, okay? Rest, okay? So in this case, I have a Hamiltonian, okay? Defined by this, okay? And curve state, okay? You have x1, x2, then you have lambda 1, lambda 2, okay?
So can we clarify the problem? So here we have a mass, and I mean the physical problem is gonna be we have a mass, then we have a force U that we are applying to it. The force is constrained within 1, but we are trying to minimize the time of the time to reach 0, to reach like when the mass goes to a stationary state, right? When x
then in the minimum time.
Yeah, in the minimum time. So the trivial answer to that is just use 0, right? We don't put any force to it, then it's not gonna move it.
No, you are not originally at 0, 0. You are originally there. Then you come over here.
So the initial condition is not 0.
Of course.
Then we have an initial condition.
Yeah, then how you apply the control.
Okay.
So it's called bump. So basically, let's say this way. I have originally I'm here. I want to go there. I want you to go there in the fast possible time. What do? You press pedal to full, accelerate. Then you press pedal to negative, like pull, right? Push and pull, right? So at a certain point you switch mode, so that you exactly stop there. Okay? We only know from this state to that state, right? From here to there. But there are multiple ways I can slowly move, but I want you to move there in the shortest possible time. Okay? The shortest possible time. So that's the idea.
Yeah.
Okay. So we don't know what is my capital T in this case. So we need to minimize that. So then you can solve. I'll go very quick. Otherwise, it's too slow. So in the end, you can solve. less than or equals to that, any positive that, so the U star has to be like using a sign. If lambda is already 0, then you cannot. So, and it counts lambda 2 is linear, so in this case, the U star, the best optimal is like you switch once. You cannot switch, like push, you can, it's only one. The optimal, I mean in optimal, so you only have one. So this can be proven very rigorously, okay? So then you can do, this is position, this is speed. You want to, from whatever initial state in here, so you are going to go this way. So it's called switching curve. So this is your 0, 0, 0, 0. Go from here to here. So the phase trajectory is like that. So we have 10 minutes. So these are, I like this second book very, very much. I like this guy very, very much. He wrote a book and he maintained a very important package called SOS, Software for Optimal Trajectory Solving. So you know that we have lots of astrodynamic missions. So like where to switch the trajectory, there's some optimization in there. So he did all of that for NASA in the past. And I just discovered recently that he started, he retired, and he started a company. It's called Applied Mathematical Analysis. So he's doing the service to do optimal control of dynamic system described by differential equations, optimal parameter estimation or inverse problems, and so on and so forth. And his software is called SOS. Okay, SOS. I believe that software is well tested within the NASA, very large scale optimization problem, dynamic optimization problem. And for documentation, to my good surprise, that he has a survey on numeric methods. So, but I really liked this one, a collection of optimal control test problems. So I attached this one to the lab 04. So I wish you will pick up. It's about 350 pages, maybe 80. And he collected different types of OCP problems. Yeah, 350 pages. So pretty good. And also, for numerical optimization, he has a survey paper about 56 pages, like written 20 years ago. Okay, 20 years ago. Okay. He's very good. Yeah. I had some emails with him 20 years ago. Okay. So I think these two books are good. Calculus of variation, there are many books. Optimal Control, Lewis, 97, is okay. Yeah. So what I'm going to do next is to quickly go through with Rail's general OCP solver in the form of MATLAB Toolbox. So available software package, I know all these people behind. SOCS, that's maintained by John Betts, from NASA. He's really good. For static optimization, is kind of well developed. We have seen the survey on the NEORS. Can you see NEORS server? This is the NEORS server. Okay. But for dynamic optimization, it's not as mature. Okay, I have to tell you that solving an optimal control problem, so I give you OCP, give me an answer. It's not that easy. Lab 4 is for you to practice. Okay, practice. So I hope you get used to this one. Okay? Because this is the only one without compiling, linking, and to the existing library, a lot of compatibility issues. And Rails, you can see over 20 plus years, still working. Okay, still working. And the other, this is a German guy, this is Australian guy, it's NASA. So this is us. So I believe we are still very competitive, okay, in terms of the effectiveness. So, of course, discretization is important. So, this discretization is basically like you have a U of t. There are infinite points in here. It's a curve. Can we change it to some sort of set of UK? And k is 1, 2, 3, n. So that kind of discrete points. Okay, discrete points. So you have a curve. Of course, you have discrete points to represent this one. Then you can do interpolation between them, right? But interpolation is not most effective. The best thing to do is do splines. Okay. So Rails is the first rigorous spline based to do a parameterization via the splines. Okay, via the splines. And you can choose different orders of splines. Linear, quadratic, cubic splines. Okay. So, and also they can do multi-step integration. Okay, multi-step integration. Rongikata 4 is a multi-step. Okay. But most of the other people, they can only do Euler, okay, Euler. So say for example, I want to do x dot is f, x. So what they do is xt equals xt minus 1 plus delta t, very small step, times fx, okay? So this is called the Euler formula. So this is not very accurate, sometimes even not even stable. So you have to make the delta t as small as possible. So it's less efficient. And guess what? In Rails, we can even use variable step. Depending on the problem, we can change the step. So it's very powerful in that sense. Okay. So there are two types. One is called direct method, one is indirect method. Our Rails is indirect method. Indirect method is solve optimal control problem, necessary conditions. So it's an indirect method to explicitly derive the custody equation and control equation and all the transversality conditions. So this is based on custody equations. What is a direct method? Is it treat an OCP as a mathematical programming problem after discretization? Just convert them into a static optimization. Okay? So you don't need to even derive all the custody necessary conditions, but this is very inefficient. Okay? And the discretization has to be very dense. Okay, very dense. Think about like a UT, then you put like a million points to search. It's not very nice. So the parameterization, you need a lot of points. However, in our indirect method is to parameterize the control as well as all the states. So Rails is using that idea, but you need to derive all these equations. Okay? So we can consider almost everything. So it's first in the world to be able to use Rongikata integration, called multi-step method. And the finite time optimal control programs, trajectory endpoint constraints, control bounds, variable initial conditions, and free final. Your capital T can be not decided. And even your initial condition x of 0 can be also part of the optimization. So you can have n cost. So this is standard. So system function can be solved by the user by either C file and M file. So C file, the C file interface, I'll give you the library. You need to connect them. So, but that's an advanced topic. So for this lab 4, you only need to do M file interface, and the M file interface was first realized on the Windows platform by me. Okay, I know C file compilation. It's not very easy. Okay, but in 1997 I was successful to release the first version. So because we used splines instead of those discretization in the Euler's case, so we can do very high accuracy without using very high number of control parameters. So that's the benefit. Okay? And there are a lot of other techniques involved based on the theory. It's called consistent approximation. So I actually want to show you it's in the lab. I just want to show you the thesis title, Theory and Implementation of Numerical Methods Based on Runge-Kutta Integration of Solving Optimal Control Problem. It's Adam Shor's dissertation from UC Berkeley, and he did it in 1996. Okay. It's excellent work. I just heard the news a few months ago. Andrew Packard died. He's one of the pioneers in robust control. He probably is the co-author of the toolbox of robust control. It's too bad. I met him in person a few times. Shankar Sastry is still the dean of the School of Engineering at UC Berkeley. I don't know this second one. The first one, Ilya Pollack, is a famous numerical analysis in the ECE department. But anyway, this dissertation is excellent.
Is it available to us?
Yes, I already uploaded into the directory. But if you want, you can find all the stuff documented in the Rails page under our lab. Okay. So this is our lab, okay? And today I probably heard that we use Rails for MPC and Rails fraction order and optimal controls. And yeah, January 2018 is very exciting. We used the free compiler and we were able to release this there. The build was successful. Okay, so here are the dissertation and also the user's menu is here. The user's menu. Okay. If you want to take a look, basically I want you to take a look. Very clear. We use slightly different. So basically I want to find the optimal control signal U. Let me see if I can enlarge everything. Yes. I'll let you go after this, okay? So basically Rails can solve very general class of optimal control problems. So this control signal, U, the cos C is the initial condition XA. A is initial time, B is final time. Okay, A and B. So these are the new languages. X dot is H, XUT is my dynamic system, initial condition. And this cos C could be put in here for optimization as well. So in fact, my functionals is function of control and initial state. And this functional can be defined as initial condition and a condition. So it's G0 is my function to define that. L0 is my cost. Okay, my cost. My control has a bound. Okay, and remember J is M, meaning I have multiple input. Okay, so the system can be multiple input, multiple output. And the initial state is within this bound. So this bound are supplied by you. You know it. And this is my inequality constraints. TI, inequality constraints. And you have inequality constraints of, and you have equality constraints as well. Okay. So these are at the terminal. Okay, at the terminal. Okay?
And initial.
Initial and terminal satisfy these, and this state and the control satisfy this inequality. Okay. It's very general. I think it's very general. There's one thing I feel today I have to tell you that if you have a very big delay in the system, you cannot solve it. You cannot use rails directly. Okay? You cannot use it. So the best way you do probably is so these are the features. So there's only one. There's only one. There's only one shortcoming so far I can see. That is the delay issue. Okay, the delay issue. So if you have a delay in the system, you probably need to use Padet approximation to turn it into a transfer function. Then you use a state space. Okay. So that's the hint for you. Otherwise, everything should be very straightforward. You just go and play it. So I'm already in the MATLAB. How I can do that one is to set path. Can you see it? I set path. I want to add folder. Let's say add with subfolder. Okay? Can you see that? Add with subfolder. So what I do is to go to my teaching this course. This is files. Let's go here. Okay? So that's it. Select folder. So they add all the subfolders. Okay, subfolders. So then I see the PWD. You can see this is my path. I need to go to my path. So you open that. So path. This again. My dot. Oh, no. So teaching this one. And this one. Okay, select folder. So now you see PWD. So this is the Rails student. Of course, you can say I use dir, I did a directory. PWD is a Linux command to show the path. Okay. So there's a mixture of those things. Okay. So what you do is you have a Rails dem is demo, okay? The reason we use this, not demo, but dem is at certain point when MATLAB is very old, they only do 8.3 type of file name, cannot use other than that. So this is 8. So you do the demo, you will see these are C compiled demo, okay? But I really hope you are going to go to the systems, so CD systems, okay? No, it's not right. Systems. So then in PWBC, you are now in systems, okay? Within the systems, you will see different problems. Godard problem, Rayleigh problem, you have band control problem, you have this Boeing problem. It's a MIMO control. So in this case, you write MMM is a MATLAB interface. Then, okay? So then you can run it. The first one is to show whether the simulation is correct. So they are running a Rayleigh problem, okay? And so you go through carefully, you run all the demos, okay? Then if in your computer, you end up to see the figure like that, that's correct. So you can see the terminal state is not at 0. But then in the optimal control, you can force it to 0. Yet some other cost is minimized. So this is like a first order approximation, second order approximation, and third order approximation. So you will see if you see these three things, like piecewise constant, just the linear interpolation, linear spline, okay? This linear spline is much better than the interpolation. Quadratic spline is the yellow one, is much smoother, much better. So if you see this, then that means everything is working in your computer. And the second one is to run the Rayleigh problem. So you can see that linear spline solution on the uniform grid, and they will end up exactly at 0 as a terminal constraints, okay? And you can add, so these are no unconstrained or unconstrained. And then I want to add bound of control, and I control bound, and add terminal constraints. So the terminal constraints add to 0 in here, and here endpoint constraints. So spend some time, then you will be able to do lab 04. Then you will be an expert on solving OCPs. These are very useful for everyone's future career, I believe so. Yeah, I hope I can spend more time with you about the codes, how to set up the codes. But you should be able to follow that. So I'm going to stop here. I hope you are good Thanksgiving break. I'll see you next Monday. Okay, that's December 2nd. Okay, we are going to have a research seminar to be given by Professor Lee, right? Okay, happy holiday. Good to have you. Then also we also did this Mesa box Peltier system lab. I hope you go through the MAD cycle, understand the modeling and the model uncertainty quantification, especially for nonlinearity exploration. Then the second is the analysis to see what are the nominal performance and what is the robustness bound, how much we can tolerate using the small game theorem. Then third part is the design. You can use a lot of designs. Okay? But I hope you do at least one H infinity based, the worst case do that. And to compare with baseline performance diagram equals 2. Go and check the files I already uploaded. From now to 20s, we have 3+ weeks, okay? almost 4 weeks. Okay. So to do 2 labs, I think it's reasonable. Plus a presentation about your FISP. If you feel like, oh, the time is not very enough, we can consider to do the presentation in another time. I will discuss with everyone. 11th, maybe it's a little bit pushy. Maybe. I'll think about it. Okay, let's stop here. Happy holidays.